So let us look at geometric isomerism. Geometric isomerism happens in compounds which have the same molecular formula and the same bonding of the carbon atoms to other atoms, but these atoms have a different orientation in space, as in they are arranged alternatively. We'll talk about what that means in a second. The thing to remember is that geometric isomerism only happens in alkenes. You need a double bond for the geometric isomerism to occur. In a carbon-carbon single bond, there is constant rotation on this bond. So what we get in that case are conformations but not isomers. You do not have to worry about the conformations just yet. So if you look at these two compounds, what would be the name of each of these compounds? Let's find the longest carbon chain, 4 carbon atoms long. So this is a butene. And what kind of a butene? Well, the double bond is at the second carbon, so this is 2-butene. What about this one? 4 carbon atoms long. Where is the double bond? At the second carbon, so this is also 2-butene. But something is off, their structures are not the same, which means that our names have to reflect this difference. What do I mean by the structures are not the same? If you look at the two double bonds, then on the first structure written on the left, the two neighbors are hydrogen and methyl group and methyl group. Whereas on this second structure written on the right, the neighbors are a hydrogen with a methyl group, and this methyl group has a hydrogen as its neighbor. So the neighbors are different. These structures, these compounds are different. In fact, these compounds have different melting points, they have different refractive index, they have a different boiling point, and so on. So several properties of these compounds are different. So we need to come up with a name, with a system in our nomenclature that reflects this difference in properties and this difference in structure. We look at the two hydrogens. In this case, the hydrogens are on the same side, whereas on the right, the hydrogens are on the opposite side of the double bond. The things to remember are that we are looking at the two hydrogens attached to two different carbon atoms, and we only look at hydrogens. So the solution we have come up with is, when the hydrogens are on the same side, we call it a cis isomer, and when the hydrogens are on opposite side, we call it a trans isomer. So the names become cis 2-butene or trans 2-butene. In general, you will see that the cis isomers have a higher boiling point, and this is because there is a net dipole moment on the cis isomer, whereas in the case of the trans, the dipole moments cancel each other out. Don't worry about this just yet. We will spend some more time talking about the properties of organic compounds, and we can take it up at that point. So again, to recap, cis or trans, the system only works if there is at least one hydrogen on both of the carbons that are part of the double bond. So the question comes, what if there is no hydrogen on both of those double bonds? Let us look at an example like this. So we see that this is also a butene. There is a 2-butene, and there is a chlorine atom on each of those carbons that are part of the double bond. But because there are no hydrogens, we cannot call this cis or trans. However, there is a way to make another compound where you have a carbon-carbon double bond. Let's keep one carbon constant, a methyl group on one side and a chlorine group on one side. But what if I change the arrangement, the spatial arrangement of the atoms, and make this other compound? Well, even now, the longest carbon chain is 4 carbon atoms long. The name would still stay 2,3-dichloro-2-butene. And this time, my cis-trans system does not allow me to distinguish between these two different molecules. So now we come up with another system which is called the EZ system of nomenclature, and in this case, to each of the atoms we assign a priority as high or low based on what are called the cahn-Ingold-Prelog priority rules. So these rules state that for each carbon atom attached to the double bond, you look at the atoms directly attached, and the atom with the larger molar mass gets the higher priority. If the atoms are the same, you move further away from the double bond until you find something that has a greater mass. So now using this idea, let us go back to our original example and figure out which has the higher priority based on molar mass. So, the thing to remember here is that you will compare between atoms on the same side of the double bond. So, we'll compare these two and then we will compare these two for their higher priority according to the cahn-Ingold-Prelog system of nomenclature. These two and these two. So, let's see. When you compare between chlorine and the first atom connected here is carbon. So, the comparison is between chlorine and carbon, not the entire methyl group. We're not looking at the methyl group. So, we know that chlorine has a higher molar mass. So, chlorine gets priority 1, carbon gets priority 2. Again, on the other side, your comparison is still between chlorine and carbon. So, chlorine gets priority 1, carbon gets priority 2. So, we see that the two higher molar masses or the two high priority groups are on the same side. In this case, so when two high priority groups on same side, we give the letter Z standing for Zuzman, and if the two high priority groups are on opposite sides, we give the designation E, antigen. So, because the two high priority chlorines are on the same side, this isomer becomes Z, and in this case, going back between chlorine and carbon, chlorine is high priority 1, low priority 2. Chlorine is high priority 1, low priority carbon 2. And again, these two high priority groups are on opposite sides, so they get the designation E for antigen or anti each other. Taking another example, you look for the group with the highest priority on one carbon and the group for the highest priority on the other carbon. So, who has higher priority between this bromine and this carbon? Well, bromine is high, this carbon is low, or you could write 1 and 2. And again, bromine is high, this carbon is low, and then we see that the two high priority groups are on opposite sides of each other, are not neighbors of each other for these carbons. Therefore, the name would be starting with the designation E for antigen on the double bond. This is still a butene and this is 1,2-dibromo 2-butene or but2-ene. Just to practice, how would you decide which is the higher priority group between a methyl group and an OH group? So, looking at the first atom, carbon, oxygen. Oxygen is the heavier atom, therefore, oxygen will have the higher priority. What if we wanted to compare between, let's say, an NH2 group and an OH group? Well, again, between nitrogen and oxygen, oxygen has the higher molar mass, therefore, higher priority. If you had something like a CH2, CH3 group on one side and on the other side, you had a CH2 Cl group. Then you would start with the carbon, they are the same, there is no difference. So, you move on. There is two hydrogens, no difference. So, you move on and the next atom is a carbon on the left side, but a chlorine on the right side. Therefore, this group has a higher priority compared to just the regular ethyl group. So, in order to find the higher priority, you go one by one through the atoms looking for the first point of difference again in molar mass. Let us look at some general cases to understand or derive a rule for whether there is geometric isomerism or no geometric isomerism is present in a particular compound. So, let's take this example. If you had a carbon-carbon double bond where you had one carbon having two groups that are the same and the other carbon having two groups that are the same. So, now how do we decide if there is geometric isomerism here or not? So, the easiest way to do that is to keep at least one carbon constant. So, I will just try to keep the left carbon constant every time and change the groups on the right carbon. So, you have AA keeping that constant. Let me change the group. Let me move this B to the top and this B to the bottom. What do we notice? Well, In the first case, you had AB as neighbors, and now also you have AB as neighbors. And here as well, you had AB as neighbors and you get AB as neighbors. My bad. So because when we changed the groups, the neighbors did not change, we say that there is no geometric isomerism possible in such a case. Let's look at the case of a carbon-carbon double bond, two groups that are the same on this side, but how about we have two different groups on the other side? Again, in order to see whether or not geometric isomerism exists, let's keep the left carbon the same and let me flip groups on the right carbon. So I get D and B. And now let me check for neighbors. Who were neighbors the first time? We had AB as a neighbor. Okay, but I again have AB as a neighbor on this side. I had AD as neighbors and I still have AD as neighbors. So even though I switched the groups, the neighbors did not change, which means you do not have a different molecule. This is still the same molecule, and we say no geometric isomerism possible. Let's look at a third case. So you have a carbon-carbon double bond. On one side you have AB and on the other side also you have AB. Now doing the same thing, keeping one carbon constant and changing the bonds on the other carbon. So I change my groups, I switch my groups around and let me go looking for neighbors. Well, I have AA as neighbors here. Can I find any other place where there are AA as neighbors? No. I have two B's as neighbors. Can I find any other place where the B's are neighbors? No. So these two are actually two different molecules. So by switching my groups on the second carbon atom, I have actually now created a different molecule. So this would need a different name. So assuming that A has a higher molar mass than B, I can say A is the high priority group here, B is the low priority group, A is the high priority group, B is the low priority group. So this isomer is Z, where the two high priority groups are on the same side, whereas on this side, A is the high priority, low priority, low priority. So this would become an E isomer, and the one on the top was a Z isomer. So in general, we can say that if you switch groups and neighbors do not change, then there is no geometric isomerism. And if you switch groups and the neighbors do change, then yes, there is geometric isomerism possible, which basically comes down to saying that if even one of the carbon on the double bond has the same groups, no geometric isomerism is possible. So let's just practice. You can pause this video and try for yourself. Can you decide whether or not there is geometric isomerism possible in these following cases? Yes, no, yes, no. In the cases that have yes, what kind of geometric isomerism? Because there is a hydrogen present on one side, but there is no hydrogen present on the other side, the only kind of geometric isomerism possible here is EZ. The same here, there is only EZ geometric isomerism present. In general, everything that is cis-trans can also be labeled as EZ, but all EZ cannot be labeled as cis-trans. So if I'm not wrong, you are never incorrect in using EZ nomenclature, but cis-trans only applies when you have hydrogen present on both the carbons of that double bond. Okay, so let's take a few examples for geometric isomers. This is from Geometric Isomer Practice 4 from the class handout. Let's just take these last few ones. So looking at number C, we see that there is a double bond, and on the double bond at this carbon on the right, you have two methyl groups. So that right away alerts you that it is not possible to have any geometric isomerism in this case. So no geometric isomerism. Then let's look at the next one. So here on the carbon on the right, you have two different groups. Carbon on the left, you have two different groups. So yes, geometric isomerism is possible. And then comes the question, because you have two hydrogens, you can use cis-trans isomers, and because the two hydrogens are neighbors for each other, you can say this is cis. Now, could you do EZ isomerism? Yes. So we could look at the priority, which is heavier, carbon or hydrogen? Carbon. So carbon gets priority 1, and here as well, the carbon gets priority 1 over this hydrogen. So in that nomenclature system as well, this would be Z. The rest of the name is similar to what we have been doing all this while. So this would be cis 1, 2, 3. You would give 3 to the double bond. So the name becomes cis 7-bromo-hept-3-ene. Okay, let's try the next one. So on the double bond, you have two different groups on the left carbon and two different groups on the right carbon. Therefore, yes, you can have yes, you can have geometric isomerism, and because you have the two hydrogens on the opposite side, this is trans. Going to part H. So on this carbon, you have two groups that are exactly the same. On this carbon, they are different, but if even one carbon has two groups that are exactly the same, then you cannot have geometric isomerism. Part I, this carbon has two different groups. This carbon also has two different groups. So yes, there is geometric isomerism, and the question is, can it be cis-trans? Well, you have a hydrogen on the first carbon, but there is no hydrogen on the second carbon, and cis-trans isomerism is only about hydrogens. If the hydrogens are on the same side or if the hydrogens are on different sides. So no cis-trans here, but you could have EZ nomenclature. So we could look at the mass of this hydrogen and this carbon. The carbon has higher mass, therefore higher priority. But here you're looking at the chlorine and the carbon, and the chlorine has higher mass and hence higher priority. Therefore, this would be Z, and the name would be 1, 2, 3, 4, 5 Z3-chloro-2-pentene. And lastly, let's look at J. So this carbon has two different groups. They are not both methyl groups. And then this carbon also has two different groups. So yes, there would be geometric isomerism. So yes, geometric isomerism. Since there are not hydrogens on both the carbons, then this is no cis-trans. And we would have to use EZ nomenclature. So let's go ahead and figure out the priority. So there is carbon, they have the same mass. So we move to the other atoms attached. So there's 3 hydrogens, but here you have 2 hydrogens and then 1 chlorine. Therefore, this gets higher priority. And on the other side, you see that there's a carbon with 2 hydrogens, a carbon with 2 hydrogens. No difference in mass. Then we move to the next side. So this is a carbon that has 1 hydrogen and 2 carbons attached to it. So a way of thinking about this, maybe I need more space for this. Okay, so to compare these, you can think of this second carbon here as being attached to, there is a hydrogen and there are 2 carbons that it is attached to, carbon prime and carbon double prime. Whereas the second carbon here is only attached to 3 hydrogens. Therefore, the one on the top, this whole group gets higher priority and this ethyl group gets lower priority. I'm just taking so much time to say this because sometimes students, when they misunderstand the rule, tend to look at the whole of this isopropyl group. And they sort of start thinking that I'm looking at the mass of the entire isopropyl group, and because the isopropyl group is heavier than the ethyl group, therefore it's getting priority 1. I mean, you get the same answer in this case, but the reason is wrong, which means you might make a mistake somewhere else. So the reason this gets higher priority is because this carbon is attached to 2 other carbons. Okay, and then coming back to the name, because the 2 high priority groups are on opposite sides, this would be E, and the whole name is, E. So let me put up a clean version of this to get the name done. So then the name becomes E, and let's do the numbering 1, 2, 3, 4, 5, 6, the longest carbon chain, and you have substituents methyl, methyl, ethyl, chloro. So the name is 1-chloro, 3-ethyl, 2,5-dimethyl, and I didn't leave space for myself, but 2-hexene. I think we'll stop here. There's lots of practice posted on the class handout.